Language modeling. So the base model of ChatGPT-4 is trained by our fundamental equation of deep learning. This is the unconditional cross-entropy loss. So as we said last time, in this case, y is a block of text, or a simpler thing to think about is y being a block, as being a sentence. And we're simply sampling a block of text from an enormous corpus and computing the log probability of that text according to GPT-4's model. So we think of a fixed vocabulary of tokens. Now a token can be a subword unit, and that's useful if you've got a name in a foreign language. You can represent it as a sequence of small units. Question?
Sorry, just fundamental equation. With ChatGPT and a lot of the language models, we're still providing the prompt. So it seems like there's still a conditional happening.
We'll talk about that, but let me say that. Let me get ahead and say what you answer the question. So there's two kinds of language models. Ones that are called decoder models. So they're used to generate the words as in generation time. In generation time, you're always predicting the probability of the next word given the context, given the words up to now, and you extend it and you generate. That's called a decoder. There's also, in the original machine translation model, there's an encoder model. The encoder model is taking the source sentence, and that source sentence can be, in the transformer, you process it all at once. It's still an auto, we'll talk about this, but you look at the whole thing at the same time. You're not slowed down by having to generate. GPT-4 is a decoder-only model. So although you're giving it a prompt, it was trained just by decoding a decoder-only model on a block of text. Does that make sense? So
I'm sure it will later.
okay. People talk about encoder models and decoder models, and whether your model is encoder or decoder. Most models these days are decoder only. Okay, so we've got some finite vocabulary of tokens. We're talking about blocks of text. A block of text is a sequence of tokens. I forget what, I mean, GPT-4 can do several thousand tokens at least, I think. So we've got the population distribution. That's the text that's appearing in the wild, on the web and in the newspapers. It's a structured object. So this is an example of computing probability distribution over a structured thing. Something that's enormous. The space of possible blocks of text is exponential, astronomical. So the way we handle structured, or a way to handle structured outputs, it's not the only way, is autoregression, autoregressive models. So in autoregressive language models, we're predicting the next word. Jeff Hinton just gave an interview at 60 Minutes Sunday. I don't know if any of you have seen it, but one point he made was that when you're predicting that people, you make the same point that I often make. When people say, oh, it's just predicting the next word. How can it, learn to understand language by just predicting the next word? And he said the same thing I always say. To predict that next word, you have to be thinking ahead. You have to be understanding what's going on behind you, in your context, and you have to be sort of understanding it and thinking about where it's going. And yes, it's per word, but to get that perplexity or bits per word down to this rock bottom score, you really have to know what's coming, what's going on. Okay, end of sequence tokens. So when you talk to ChatGPT, it goes on and on, but eventually it stops. I would give it, 2 sentences and it would give me 5 paragraphs. But eventually it stops. So it stops by generating an end of sequence token. So there are two things. When we start talking about GANs and VAEs and diffusion models, there's going to be a couple things we want our models to be able to do. So you want your model to be able to take an input, like a block of text, and compute a probability for that. Right? So the way this thing is trained is it computes a probability for a block of text by multiplying together these individual probabilities. The other thing you want to be able to do is to generate text. And the nice thing about these autoregressive models is that they can do both. So at training time, we're just computing a probability. At generation time, we're actually generating the words one at a time. We're using the chain rule to sample from a next token. There's a lot of subtleties in generation that we'll be talking about later. Okay, word embeddings. This is really token embeddings. Here W, this slide is calling it a word. In reality, it's just one of these tokens. Almost all the common words of English, the standard words of English, are single tokens. So you only get subword units if it's a really unusual name or a very rare word. Okay, so we've got a token or a word W. This E of W was on the exam, is an embedding for W. And I write it using Einstein notation so that this is a vector whose indices are from I. You can view this as a dictionary that takes a word and gives it a meaning. A meaning is just a vector. Right?
So this embeddings are also learned. Could
The
you say a
embedding is
bit
also
about how
trained.
you go about that? Like, do you train both the embedding and the generation together, or are they separate pieces?
Did you take the exam?
I did take the exam.
Part of the exam was to train the embedding.
Yeah, no, but I'm just saying in practice.
In practice, yes,
Yeah.
the embeddings are trained.
Okay.
Okay.
So the embedding kind of maps like one word to just multiple things which are often contained in a vector, and like each word is mapped to sort of like the same number of different things.
Same number of numbers. It's a vector, right? So you take the word and you map it to this 1,000-dimensional vector. It's somehow capturing everything you need to know about that word. Another thing Hinton said, which I've been saying for a long time also, is that you can make an analogy that deep learning, SGD, is kind of local search, and you can make an analogy between machine learning and evolution. So he said, understanding machine learning is like setting up the rules for evolution, and then you just see what comes out of it. And setting up the rules for evolution doesn't mean you know or understand what evolution is going to produce. And so that's sort of the situation we're in. So what are these? So yes, we're mapping a word to a vector that's representing what you need to know about that word, but that's sort of all I can say.
I have a question about the analogy with evolution. Like typically in evolution, like the landscape is not fixed, right? Like if it's multi-species, then what you do best would be dependent on what like the other species are doing. And here, like on the given probability distribution, the loss is just fixed in time, and then you're descending.
Well, if you think about your own worldview belief structure, there are all these beliefs and there's logical coherence and everything's connected to everything. It's sort of like it's a very complex, potentially a very complex thing to learn the semantics of language. Okay, I'm going to go over this fairly quickly. I think RNNs are still used occasionally, but we talked about this last time. So you can build an autoregressive language model with a recurrent neural network. So the recurrent neural network is going to can take, say it takes a sequence of word embeddings in, so it's taking a sequence of vectors in, and it's going to produce a sequence of vectors out. And I can take this vector out and define a softmax over the vocabulary, and I can actually make this into a language model. Right, so on the exam, you were taking the inner product of a word embedding and a hidden state. So I could do that with these hidden states to get probability distributions over the next token. Now, vanilla RNN is just, the simplest thing is just one layer of a multi-layer perceptron. This is the, sorry, let me go to the next slide. Just one layer of a multi-layer perceptron. So this second hidden vector, say, is computed from the second word embedding, and the previous hidden vector just by incorporating them both, a linear sum for each of those inputs into the input for a linear threshold unit, a neuron that would produce the next hidden vector. Question?
The WHHs, do they vary as you move along
No, that's a good question. Not in an RNN. So the parameters in this model are fixed. So you're feeding the same model again and again. Okay, so you get the same problems in RNN that you get with deep neural networks, right? You could think of time here as analogous to depth. You're going through many layers of this network. And I'm going to skip over the gradient clipping. That's a technicality. Time as depth. So what you'd like to do is have something analogous to residual connections to more directly connect this. This is the hidden state being passed on. This and this are the same. You would like to directly connect that hidden state and be able to pass it through like a residual connection to the next hidden state. And that's done with gating. So what a gated RNN does is it computes a gate, right? So there's a linear threshold unit that computes a gate value. The gate value is deciding for each dimension, so the hidden vectors and the inputs will assume they're the same dimension. The gate is deciding for each dimension, do I pass that dimension through directly, or do I replace that dimension with the input, or do I add the two together? Right, so the gate value is, if the gate value is a half, then the two inputs get added together like in a residual connection. So a half would model a residual connection. But the gate's allowed to say just pass the hidden state through, or just pass, or forget the hidden state and just do the input. And so gated RNNs were the state of the art before the transformer up to 2017. And in particular, this LSTM, which was invented in '97 by Schmidhuber, became a super big deal during this era. Are there any questions about RNNs at this point? Yeah.
Is there one set of gates for the entire MLP, or is it so like did they do so during like training? The same gate is used to compute like the amount of the hidden vector and hidden vector. Like is that gate, are those gated combinations the same set of?
They're actually computed. I went over this slide a little too quickly, but you've got these two inputs. This is the simplest gated RNN. And you've got these two inputs. You've got the word vector and the previous hidden state. And those two inputs are fed into a linear threshold unit to give you, this is going to be the computed thing from the, this is going to be a newly computed value. You also take the gate, so you compute the gate and the newly computed value. So you're computing both the gate and the newly computed value, this newly computed value. You're computing these two things every time from your two inputs. And then you're using the gate to control the information flow. Yeah.
For this updating the gradients, is it after we predict every token, we will do a backprop?
So at training time, you're given a whole sequence. And the probability is a product of these conditional probabilities. And if you take the log of that, you get a sum of each individual prediction. So you get a loss term in every prediction. Does that answer your question? You back propagate. Now, in this case, you're back propagating, the parameters of all of these are the same. And so the gradient is being accumulated on the same set of parameters as it's going backward in time. Yeah.
Thanks.
Is there any meaning behind the letter choice R? It doesn't look like it means residual to me.
if the gate is always a half, the gate is being computed, so it's anywhere between 0 and 1.
Oh, I'm saying, why did we choose the letter R?
Oh, why, that's a good, for residual.
But if I understood the previous lectures correctly, a residual just connects the input to the output. So here, the HT minus 1 term looks more like a residual because it more like passes the previous layer thing down to the next layer unmodified.
This is like, so if this was a residual connection, it would just be the sum of the two black parts. Right, and this would be the previous layer, and this would be the residual thing being added to it.
So the residual is also modified in some way. Like it's at least passed through a activation function.
The point is, if the gate is 1/2, it's acting like a residual connection.
Okay, yeah, I'll take that.
Oh, and just to point, back in the day, people would use bidirectional RNNs, so this is going to be both forward and backward. In every position, you concatenate the forward and backward. Use multi-layer RNNs. Modern versions of this would have residual connections up the stack of RNNs. So here's the input, here's the first RNN, and you stack that on top of the second RNN, and so on.
So the residual connection be at each, and like at each layer there'd be a residual connection as you go through the depth.
So now we have, people talk about highway interchanges. Now we have the depth of the RNN, and we have time going this way.
So would
And
there be
so-
residual along the time and the depth?
No, so along time, we still have gating. So
Oh,
along time, we still have gating, because it's still the same network at every time. But we have residual networks in depth of that RNN. Okay, so we talked about this last time. So this was a paper that appeared in 2014. I talked about the speaker and saying minimal innovation for maximal effect. And what happens here is you take the input sentence and you run an RNN over it in reverse time in this paper, so that the hidden state you get out of the back here becomes the thought vector for the input. And then, now you've got one, in this paper, there's one vector representing the entire input sentence in translation. Going English to French, you've got this thought vector. You use that as the initial vector in a generative model in Generate French. And this model is a different model. It has different parameters than this model. This is the encoder model. That's going to give you the thought vector. And this is the decoder model. That's going to do the translation into French. Okay, so this is a structured conditional case. Attention. This is where we ended. So attention was introduced about the same time in 2014. So this is now roughly 3 years before the transformer. So attention predates the transformer. So in this paper, and I said this paper appeared almost exactly simultaneously with the paper I just talked about, except it introduced attention. So this is what this paper did in modern language is called a cross attention. So we're going to generate, we're going to take our input sentence, and we're still in the era of RNNs. We're going to take our input sentence and we're going to use an RNN to construct a vector at each position in the input sentence, right? So you've got a vector at each place. As we're generating the output, intuitively, when you generate an output word, it's typically coming from some input word in the input. So that's, you can think of that, or it's called an alignment between the output and the input. So what we're going to do is put an explicit alignment mechanism into the model. And that's done with cross attention. Okay, so we're still, in this paper, we're still gonna have a thought vector. We're gonna have a sequence of vectors. So here's our thought vector for the input. We're gonna have a sequence of vectors associated with each input token, each input word. Right, so this is our sequence of input vectors. We're also gonna construct the sequence of output vectors. Okay, now here's the key idea behind attention. This is across attention. So you take an output position, and the output position, you want to know, what am I translating next? Where in the input sentence do I find the information about what to output next? So this attention is saying, for this output position, where am I looking in the input? And this is a soft attention. So it's a soft max over the input. Okay, so if you think of a soft max is taking a set of something and defining a probability distribution over that something. Like when you have a softmax defining an output label, it's defining a probability distribution of the output labels. Here, we're at a given point in the generation process, and we're weighting a soft attention, we're weighting the input positions by a weight. So alpha T out T in is the weight at time T out that we're putting on each position T in. And it's important that this is soft. It's not a hard attention. You're not saying, I'm picking that word. And that's going to really help. Making things soft always really helps the SGD, because it can be non-committal and still just figure out where, eventually the SGD will learn to focus more tightly. So I've got this, so now for each out position, I've got a distribution over the input as to where I'm looking. Okay, and then what I do is, remember, each input position has a vector. Now that vector is actually used in computing this distribution also, right? So to know the score, softmax converts a score to a distribution. To get the score of this input position, I'm going to take an output word, take its embedding, and take an inner product with each of the input positions. Right, so that's going to give me a score for each input position, and that gives me this, I convert that score to a probability, and that gives me this attention soft weighting. Then I take that soft weighting and I weight the input vectors. This is now a weighted sum. I'm using that capital T for an Einstein notation to represent a weighted sum. So I'm at a position in the output. I've got a weighting over all the input positions. Each input position has a vector. I weight those vectors by the weighting of the attention and add them. It's an averaging over that convex combination, over that probability distribution on the inputs. So that gives me an output vector at T out. Then I'm going to predict the next word in the translation. It's a generation model. I'm predicting the next word as a function of the thought, and I'm not going to give you detailed equations for this, but the inputs for this prediction are the thought vector of the input sentence. This out I computed, right? I computed an out at time T out. I computed this representation of the input appropriate at this time. This is I've got an RNN running on the output also. This is the RNN state running on the output. This is the vector computed from the weighted sum of the attention. So I've got a thought vector, what the RNN computed as it's running over the output, and this weighted sum over the attention, over the input vectors. And I take those three pieces of information to predict the next word in the translation. Questions at this point?
What is the H thought, the tilde?
Here?
In the last line, H thought has a tilde.
Oh, there's a tilde. That tilde, that's a typo. That tilde should not be in each thought.
And you terminate this sentence by sentence, like all the conditionals.
So this is doing the chain rule, right? It's predicting one word at a time.
But its window is a sentence. Like you'll add one vector slowly in the translation. When the sentence ends, you reset and
When it generates an end of sequence token, you're done.
yeah. Okay.
Lots of issues in generation that I'm ignoring.
What is the weighted sum doing here?
Suppose when I'm generating a word in, let's say I'm doing English to French. Suppose when I'm generating a word in French, it's actually a translation of a particular word in the input sentence. You'd like to know, as you're generating it, you'd like to look at that word. Right? And you'd like to have the information about that word. So a hard attention would say, as I'm generating this, I'm going to translate that word. Soft attention says, as I'm going to generate this, I don't know which word I'm looking at. But I'll put a probability distribution over which word, over the words that it's likely to be coming from. Does that answer the question?
Yeah. I guess, are these like agents coming from like an RNN's like multiple hidden states kind of thing, or like how are they being computed?
So I'm sure they had layers of it. It was one of these stacked RNN things. So this stacked RNN is still an RNN, right? So it's still computing a vector at every position. Is that?
And so then the H-out's like the weighted sum of all of the various hidden states, but that's like specific to this.
No, but there's a top hidden state. And it's not. These
Oh,
are.
I see.
See, this is the input tokens, and this is what is being seen by the translation system up at the top here. Yeah.
So the H tilde out is only about word WT out, but not the words before it, right?
Right.
This brings the question of like, are you considering any word that's like not input but not W out, right? Like, cause like when cause like given a prompt, like you are spitting out a lot of words, so like, but right now all these computation only involves the exact previous word, but not the previous word stuff. Where
Well, this W out here, this. Some setting somewhere. This H tilde out
yes,
is a weighted sum across the entire input sentence.
yes, but it's not including any output words except for the WT out, right?
Right.
So what about the other outputted words before it?
You know, I would have to go back and check the paper.
Okay. Also, like, what's
The way I'm writing these equations, it is keeping track of its state as it's outputting. But the way I've written these equations, it's not doing attention on the over the segment generated so far.
Oh yeah.
This is inspired by the alignment issue in translation, right? The alignment issue in translation is ancient, right? As I'm generating in a phrase-based translation system, you're always taking a piece of the input and moving it to the output translated.
Oh, okay. So it's more like as long as I know the exact previous word, like then I know where I am at, and then like I'm able to like decode the next one. So like if it's not like generation, but more like translation.
Right.
Also, the question is like, what's the H out without tilde?
That's so you are generating with an RNN. As you're
Okay.
generating with an RNN, that RNN is computing a hidden state at each position as it generates.
Oh, okay. So like the H tilde is calculating the relationship with the original text.
The
And,
alignment, right.
Okay.
H tilde is about the alignment and H is the state that as it's going along.
gotcha. Thanks.
Question?
Could you describe what is WT out again? Is that the embedding the station previously?
So as we just mentioned, so you're going through the output generating one word at a time. The words you're generating have embeddings. All the words have embeddings. So EW out is the word embedding of the French word that you're generating. And this is the this, before you generate the next word, you're going to use the most recent word you've already generated to define the attention, to define the alignment, as part of defining the alignment.
That's represented by the H. In the equation.
Sorry, that's right.
So you're basically just computing the attention is computing the attention that's
This W out in every position in the input sentence. How much attention is this W out paying to this position in the input? Okay, this is just a fun thing that appeared at this time, shortly after this paper appeared. This is still 2015. Image captioning. So in image captioning, you take an image and you write a caption. So you can think of this as a translation problem, right? It's exactly taking a structured input to a structured output. You're taking an image to a caption. So you're going to generate that caption one word at a time using an RNN. And if you use this, methodology, then as you're generating each output word, that output is defining an attention with the image, right? So I'm going to construct an attention over the image as I'm generating the output words. Am I making sense? Think of this image as the input sentence. You're generating an output sentence. Each time you generate a token in the output sentence, you're constructing an attention over the input. And so what you get is, as you're generating the word frisbee, you're paying attention to the frisbee in the image. And as you're generating the word girl, you're paying attention to the girl's face in the image. Yeah.
What does the attention look like for the articles in that? In the
I don't know. Probably not good. But this was just a fun thing done about the same time. Shortly thereafter. Okay, the transformer. Finally, the transformer. We're going to see what GPT-4 really is. There are lots of details, but this paper, the transformer paper, appeared in 2017. We're going to replace RNNs with self-attention. So,
Two slides to the equations. Like here we want to do a weighted sum, but you want to like transform it to the other language, right? Or
right.
when you do the twiddles, you're still doing a weighted sum over the H ins.
So this there's an inner product expressed right here. This is the score between a word in the output and a word in the input. And that score is assuming that these two vectors are sort of in the same space.
And so after this is done, you would have another layer that takes in your H twiddle outputs and turns them into words.
Well, there's the process of generating the next word. And that's going to take this H tilde as input. Right, so it's taking, you can think of this as an ambiguous representation of some of the input words. If this was a hard attention, it would just be the vector of some input word. So you've got some focused average over the input words that get used in predicting the next word. Okay. So, the transformer has a residual stack. So the last problem on the exam was this abstract residual stack. The transformer has this residual pathway. And what I'm going to do is try to define each one of these blocks. One of these things is called a block. And what I want to say so the input vectors, so there's a sequence of you have a sequence of tokens in training, right? The sequence of tokens, you've got a vector for each token. I'll come back to this in a minute, but what's gonna happen is the transformer treats the input vectors as a bag. Transformer does not have any natural order on the input. So to give the input elements order, you append what's called a position embedding. We'll come back to that. I'm not sure I should have introduced that at this point. So the input is the sequence of word embeddings augmented with a position indicator for each word embedding. This is what it looks like. So these are blocks. You've got words at the bottom coming in, the word vectors. There's something called there's the self-attention, which we'll talk about in a minute. Then this is a residual connection. The add is a residual connection. There's a normalization, these layer normalization. There's a normalization at the next layer. Then at each position, over each token, there's a two-layer MLP, multi-layer perceptron, that massages, that processes the information over that layer, over that word. So the nonlinear processing is actually in this step. Then you do a residual connection around that, and again, add and normalize. There's another layer normalization there. And then you stack, you take this whole thing and you repeat it, I don't know, GPT-4, something like order 20 of these layers, of these blocks. Okay. I'm going to come back to this slide. Self-attention. So what is self-attention? So what we just showed was an alignment, a cross-attention, an alignment between the output and the input. Right? Here we're going to take a sequence of words and define a self-attention. Right? So let's think of now the encoder model. So I'll assume for now that I'm processing a whole block of text in parallel. Now, that means that every word in that, since this is an input sentence, I don't have to worry about making sure that the next generation doesn't look into the future. I can look at the whole block at once, right? In the encoder model, I look at the whole block at once. What we're going to do is each position in that input sentence, say if we're doing machine translation, is going to attend to all the other positions, including itself, right? So we're going to have an attention that is a self-attention. I'm going to keep going without equations because it gets more complicated. We're going to have a self-attention. Each position is going to have an attention to each other position. And the idea here is that if I want to represent a noun phrase or a verb phrase, and I want to have a vector that is the meaning of the verb phrase, the meaning of that vector has to look at a lot of words, right? It has to look over the verb phrase. So this attention allows the next layer to selectively look at words in the previous layer. Am I making sense? I see some people looking a little puzzled. Yeah. So we've got an input sentence. What we're going to do is we're going to have a residual stack. The residual stack is computing a vector over each token up these residual layers. So suppose I want a vector at one place in this stack to represent the meaning of a phrase, like a noun phrase. Or maybe it resolves a pronoun. A pronoun, he, they, it, is going to refer to something. And you would like the vector over the it to say what it's referring to pull information from somewhere else in the sentence. So how do we get information over a given word as we're computing it to look at neighboring words, at the right neighboring words to compute the meaning at this position? Okay, so the way we're going to do that is each word at some layer in this thing is going to define an attention with all the other words. What combines with this word? What does this word combine with to produce the vector at the next level? So we're going to have an attention for each word over the other words. So this is a self-attention. The sequence is attending to itself.
Is the mechanism for computing attention like the same as before? So like the probability distribution, it's like it's a complex combination of the.
Yes.
Okay.
Yeah, it's going to be very similar, except there's a twist. The twist is that and this is my interpretation of the twist, my interpretation of what's going on. And I think this was the original intuitive motivation. If I'm going to compute the meaning of a noun phrase, that noun phrase has different parts. There's an adjective, there's a noun, there's a determiner, and those different parts play different roles in computing the vector for the noun phrase. So the idea is you're combining words in the input, but those words play different roles when they're combined to produce the vector over the position. So co-reference. If I've got a pronoun it, and I want the vector to represent what it is referring to, that's a different relationship across the sentence than other relationships, like what's the subject of this verb, right? Subject of the verb would be a particular relationship. So there's this concept of head. So the concept of head is strange because it's completely arbitrary in the model. There are some number of heads. So I think GPT-4 would have like order 20 different heads. Each head computes its own attention. So the attention is computed per head. So for each position and each head, there's an attention for that, defined by that head for that position over the rest of the sentence. So you might have a head for, a head that's looking for the referent of a pronoun. You might have a head that's looking for the subject of a verb. But that's not built in. The only thing that's built in is that there are heads, and each head defines its own attention, and the meaning of the head comes out of the training. Okay, so this is the attention. So now we're at equations. Okay, so we have, the last line here is an attention. Right, so the attention is per head. There are many heads. Each head is defining for each position T1 a convex weighting over the position T2. Okay, and this is computed using a query and a key. Okay, so think of now it's even more complicated. You think of the sequence, the sentence we're analyzing as a kind of database. And this database is we're going to query the database, and the database is going to have keys, and how much attention we place on a position is going to be determined by the query coming from the person who's asking, and the key, which is the information being provided by the other position, and the query and the key are also per head. Okay, so how does this work? So at each position, we're going to construct a query that's asking a question from that position for that head. It's getting kind of complicated. We have this head. Say it's a co-reference head. So for this co-reference head, at each position, each pronoun, where it matters, we're going to have the co-reference head. The co-reference head is going to ask a question. It's going to construct a query vector for that head. This is the pronoun query vector. Every position in the sentence is going to have a pronoun key vector. And we're going to take an inner product of the query and the key to get the weight for where we think the co-referent of this pronoun is. And I'm putting all these semantics on top, but the model is just these equations. The semantics comes from the training. Is there a question?
Kind of half question. So why do you use queries and keys, like two of them, to compute the weight vector? Like why do you split the process into two processes? to put them together? Like why not 3 or 4? Why is it only 2?
I think the intuition here is that, before we had just one alignment attention. Now we've got many different attentions. Within the same self-attention, we've got the pronoun attention and the verb and the subject attention. We've got all these different attentions. And we want those different attentions to result in different weights, even from the same position. So this position wants to get many different weightings. So to get the different weightings, we wanted to find a different inner product operation for each head. So for each head, we're getting a different attention with a different inner product operation. So we compute a query at each position, and a key at each position. And then for this head, like the pronoun head, we're taking the position of the pronoun and constructing a weight over where the referent is using this, it's off my slide. But what we're going to do is take a softmax over this position of an inner product of the query from T1 and the key at T2. That making sense? I see a lot of people kind of,
Yeah, I have 2 questions. So the first one is like, let's say like for some given self-attention pairs, if you have like 10 heads, each head is looking at the entire input, right? Okay. The second question I have is, so for each head, then, if you want, so, let's say you're like looking at like word I, for example, like the embedding of word I, then the query is basically asking like, could you explain the query vector again? I think I really understand the key, but not the query. I still don't understand what the point of the query vector is.
in some models, the key and query are taken to be the same vector. And then you just take an inner product between T1's vector and T2's vector. But in the original transformer, you have this separate query and key. So, you want to think of it as like a database. You want to think of, I'm looking for, oh God. You want to think of it, it could be that the information that you extract from T1 to say where the attention goes is different from the information you're going to extract from the position you're extracting it from, right? So you want to say, there's some information I want to get. I'm going to say what information I want to get, and it's going to say what information it has. And that may be extracted in different ways in those two rules. The question about what I want and the answer about what I have, here's what I want, here's what I have. Those can be different functions of the vector at that position. Yeah.
Can we forget about the Korean key analogy and just think of it as two matrices with parameters there, where you just combine them to figure out a certain weighting of tokens, outputs from the layers? Could that be right?
Yeah.
And that's
the equations are the equations.
Right, and that's just then building upon my previous question, why not have 3 or 4 more of the same thing, just line up each, after the query. So right now these queries and keys are 2 matrices of the same size and shape, right next to each other. Why not put 2 or 3 of them more next to it?
Ultimately, you're interested in defining this attention. Right? So the question is, how is the attention defined?
Right.
So it's natural to take the score of the attention of this head from T1 to T2 to be an inner product of 2 vectors.
Why not the inner product of 3 vectors? Am I making this a wrong idea?
You could make it, yeah.
But it's possible, right? In that sense.
But it's probably, you can always add another head.
Gotcha.
So intuitively, is Query just trying to capture the nature of all possible semantic relationships? And then
Well, the various heads are trying to capture various ways in which words are related. So if you have 17 heads, then you've got 17 chances of capturing, you've got you can possibly capture 17 different kinds of relationships between words.
Why don't you just select, so if you have like a sentence of some length, why don't you just select each word in that sentence to be?
Because well, that's too many, right? You're dealing with thousands of, the block is 1,000 long. And you know, if you want to analyze a phrase, that phrase could occur anywhere. So it's sort of like, it's a little bit like CNNs where you have this translation invariance. You want the processing over a given piece of text to sort of be somewhat independent of where that text appears.
How do we prevent all these heads from going down the same road or similar things, discovering similar things? Do you like, is there a certain smart way of
making it non-redundant? I think non-redundancy just comes from improving the model, right? If something's redundant, it's not going to improve the model as much as finding something new.
I guess like, how do we know which head to draw from? Like if we're coming from T1 and we know that like head I through head N like compute like most likely for this specific embedding, like how do we know from which head to draw for this next word?
Every attention is computed entirely within one head.
I see, but like, because I thought like the idea is like with the heads, each of them could pertain to like some sort of semantic continuation of our sentence, kind of like this could be the verb which, or like the noun which goes like with this verb or whatnot.
So another way I like to phrase this is if you think in terms of a dependency parse. So in a dependency parse, you've got a head word and an arrow that says this is the subject, this is the object, this is a modifier. So the label on that arrow is analogous to a head. Right? It's saying there's a head looking for a certain relationship between words. I don't know if that answered your question.
That makes sense.
Okay, so these are the semantics. I mean, there's this weird thing about the bitter lesson, right? The bitter lesson is the more insight you try to put into the model, the worse you work, the worse your model works. This feels like a counterexample. It feels to me like they knew what they were trying to do, and it was well motivated, and it worked. Okay, computing. So this is computing the attention. The last line down here is the attention. And what do I do with it? Well, so now there's in addition to the query and the key, there's a value matrix. And the value matrix is taking each position and computing the value that is going to be returned. So you've got the query, the key, that determines how much you're looking at a position. What's the value you return from that position? That's determined by the value matrix of that head. Right? So each position can ask a question, each position can say, here's the key to the answer, and each position can give the answer. Right? So you've got these three matrices, and the value is one of the matrices. And then I can actually apply the attention. So there's this H tilde, L minus 1. This is like the H tilde in the last model. So it's per head. And it takes a weighted combination, this capital T is an inner product. We're taking a weighted combination of the weight and the value at that position. And the ith neuron picks up the weighted combination of the ith neuron. So you're just taking that convex combination and you are adding together the value vectors weighted by the convex combination across the block.
Importantly, that was the entry that we softmaxed over in the last when calculating the weights.
This alpha,
the T that we're summing over, that's the one we softmaxed in the last slide, right?
that's the convex combination. We're summing over a set of numbers between 0 and 1 that sum to 1. That's the convex combination. Okay, so that's the essence of self-attention. Now we've got an issue. We've got some number of heads, some capital K number of heads. Each one of them is giving us a value from the self-attention across the whole sentence. So now we've got a number of value vectors that we just extracted proportional to the number of heads. We've got a value for each head. What do we do with that? Well, we concatenate them. So this is the value for head 0, the value for head k, or k minus 1. K value vectors, we concatenate them. And then we pass that through a matrix that reduces the dimension. We take this big concatenated vector. Does concatenation make sense? You just take all the components of this vector followed by all the components of that vector and so on.
I have a quick notation. We're concatenating over I, over capital I. There is the third dimension.
I is the set of neurons, right? I'm intending this to be a vector. Right? Use a capital to say that's a vector.
Okay.
And I have this vector followed by another vector followed by another vector.
Got it.
And I just concatenate them all. And then I take that concatenation and I pass it through a matrix to reduce the dimension of this to the dimension of the residual pathway. So we have to get from here to an add and normalize. This is an add and normalize. So to get from to do this add and normalize, you want this dimension coming up here to match this dimension coming down here. So you get it down to the dimension of the residual pathway, and then you keep moving up the residual pathway. Okay, finally.
Why are you squaring the? There was this h square bit.
Oh, that's a typo. I'm sorry, that's a typo. I think I was calling h tilde h2 at some point, and I didn't fix it everywhere. Okay, so now we're back to this picture. So now we've come here. Right? We've done our self-attention with all our heads. We've come here, add and normalize. Now we're going to do feed, at each position, we do an independent feed-forward layer. And this finally has a ReLU in it. Right? So here's our nonlinearity. We're going to first pass it through a ReLU, and then pass it through a second feed-forward layer, and then it goes up to the neck to this add and normalize, and then we do it all over again. And we do it like 20 times. And, okay.
Do you have an intuitive explanation for what those layer normalization points matter?
I think the explanation for that is much more general than transformers, right? It has to do with keeping the values order 1, getting the SGD to work.
Okay. Why do they use layer norm instead of batch norm or
I think the layers here are big. So you're getting a lot of averaging, especially as the models get big. And the layer norm is just, I think it's engineering-wise easier. So it just became more popular. I think that's probably the answer. That you don't have to worry about this issue of feeding it with average values at test time if you don't have a batch, because the layer norm will work on a batch of 1. So I think it just replaced. I don't know why. These things get stuck. Once the architecture is established and everybody's downloading the models, nobody's going in and diddling with the details much. So once a decision gets made, it tends to be. Also, once you've learned how to train that thing, you don't want to change it and have to learn again how to train.
Yeah. So are there multiple encoders? Like one after another one? Why is that designed? Because I understand the first one is like you wanna see the similarity between different. You wanna take thinking in the context of other words, but the next one, what does it mean?
So this is an encoder model, and I should have talked about the decoder model. So this is taking it, everybody's attending to everybody over the input sentence. When you generate, especially if you're going to compute conditional probabilities, you can't look into the future.
Yeah, I'm just asking like why are there like another encoder after you get the output of the first encoder?
I mean, why do we have this block on top of that?
Yeah,
block?
like I understand the meaning of encoder number one, but like what is like encoder number two?
Well, you're sort of letting the machine think about it a lot.
Okay.
Think about it again and again and again. Okay, and I should have said something about the decoder. So the decoder behaves differently at train time from at generation time. So at train time, you've got your whole block. And GPT-4 is a decoder-only model, meaning that it's just taking this block of text and computing the chain rule across it. There's no input. There's no notion of an input that you look at all at once. So it's a decoder-only model. And at train time, the decoding is done in parallel. You don't have to wait for generation because you know everything. All you have to do is make sure that when you calculate a probability for this word, that the attentions used for that word were backward in time. Right? So when you compute an attention, when you generate a next word, the attentions across the context, the prefix up to that point, cannot look into the future. It's called causal masking. So you prevent the attention has to be zero into the future. Does that make any sense? But you just force the attention to be zero into the future, and then you do everything in parallel, subject to that constraint. There's no waiting for generation at train time. You just calculate each conditional probability, all of them in parallel. And that's a big advantage of this architecture over the transformer. At train time, the runtime, if you've got enough parallel compute, the runtime is just the depth of the transformer. I can run that whole block in parallel. All those attentions can be done in parallel. Whoosh, whoosh.
This is just for training, right?
What?
This is just for training. Parallel, right?
Parallel for training. At generation time, you have to wait for the words to be picked.
So why is it called decoder only? Like you still have
Because back in the days of translation, there was an encoder and a decoder. And the encoder did not have to be causally masked, and the decoder did have to be causally masked. So now the word decoder means causally masked, and encoder means not causally masked. Okay, I'm about to start something completely new.
For decoder, if we have two words, then each word is producing a prediction. If a sentence has two words, is this one sentence producing one prediction? Or
So the first word has to be drawn from nothing, because it's just the probability over the first word. And the second word can be drawn by looking at the first word. So then the attention is trivial. It has to be all on the first word. And then when you generate the third word, you can pick which of the first two words you pay more attention to. The fact that first word has to be drawn, so what happens is that first word, in its vector, it can't have seen, under causal masking, it can't have seen any of the future words. So there's really very little information in that first vector. And that causes weird things to happen. But it's still not seeing the future words. So if the first word was a verb, it's not seeing its subject. Oh, I see what you're saying. Well, the model is still, the first epoch just adjusts the model parameters. Right, so the model parameters have been trained from the first epoch. But it's still defining but whatever those parameters are, they're defining some probability distribution for the sentences. And so in some sense, you can just say, well, I just want to know what probability does the model assign. So you're still left with this problem that the first vector is not computed. The first, if you have a verb initial language, the first word is a verb. It doesn't get to see its arguments when its vector is computed. Anything else I want to say about this?
Sorry, for the decoder, if we are producing one word at a time, why we need a mask? Maybe I didn't understand the masking part.
So at train time, you just want to compute the probability of a sequence. Right? Because that's your loss function, that's going to train your model. When you compute the probability of the sequence, you have to use the chain rule. What's the probability of each word given its previous words? So to compute the probability of this word given only its previous words, you can't look into the future. The attention is restricted to only go backward in time. That's the causal mask. There's lots more to say about this, and I think it'll keep coming up again as we talk about various applications. Yes.
So for this one, which has like self-attention across all of the complete sentence, like what is the score you're optimizing? Like what is the loss?
Well, in a translation model, the loss is the log loss on the y.
On the y.
It's probability of y given x. So you have to look at all of x and just what's the probability of translation.
Are there versions of this which are just decoders stacked on top of each other?
So GPT-4 is a decoder only.
And it works.
Great. I mean, this issue of, even though it's decoder only, you type something, and when it analyzes that something, it's using causal masking. So it could, in principle, not do causal masking on what you type, right? But it's a decoder only model, so it does do causal masking on what you type, but it still gets all those vectors.
Look at the two hands here, the left arrows and the right arrows.
The feed forward, blue.
No, I mean just all of the arrows. Isn't the only input the sequence of?
So the dashed lines
so what
are
is it
the dashed line, dashed arrow.
I mean what are the two inputs at the bottom?
Oh, those are just 2 words. Thinking machines. 2 words. Analyzing 2 words. Oh, the position embeddings. If you look at these equations, this attention, let's go back to so you're computing an attention here. There's nothing in this attention that knows about the order of the words, right? It's just taking every pair of words and computing it in a product. So that score between words is completely independent of where those words occur. Is that making sense? You've got a key and a value, and if we didn't put the position embeddings on the input words, the model would have no way of using position information. It can't pay more attention to them, because the model is going to, and it does, pay more attention to words near the word you're computing the attention from. The attention tends to be local, right? If you want to know the arguments in a phrase, it's a local attention. So order matters.
So we concatenate the word embedding and the positional embedding, right?
Right.
But both of those are learned by the model.
Position embeddings are somewhat special. Sometimes they're learned by the model, and sometimes they're hand-coded.
Okay, hand coding kind of makes sense. If it's learned by the model though, what's hypothetically to stop the positional encoding from learning the word embedding and the word embedding from learning the positional embedding?
Well, that, say we take the 254th word position. That's going to be the same position embedding for every block of text. It's always the position embedding for 254.
Okay, so that invariance
so it can't learn anything
constraint
about
kind
any
of forces
particular
it to.
word. Right? It's going to occur by every word.
Okay.
Yeah.
I understand that you explained why GPT is a decoder only thing. So my question would be but if you give it a prompt, it still needs to encode that prompt. But like, why is that like not an encoder then?
Well, it could be. There's no reason it couldn't be. Just it simplifies the training to train with decoder only. Because when you
But like you
and then it works. For some reason, it works to just run that decoder only model off over what you type and then let it continue.
so like, does the process of like understanding the prompts count as decodes also in this context?
So it's calculating a probability for what you typed, which it doesn't have to do.
Okay.
Right, but because that's what it was trained on, that's what it's built to do. That's what it does. It just because it's trained to calculate the probability of a block. And it's going to include what you type and what it responds with.